Okay, now we go for example number 2. Water is handled by a system of pipe as shown below. So we have pipe A1B equal A to B. So means that water from here to here and water from here to here is using the same type of pipe. So the length is 100 meters, diameter is 0.5, and the friction factor is 0.0055. And then all the types length and diameter is showing in this table. And then we found that the elevation of outlet D, E, and F. So we have three outlets here. D, E, and F is 100 meter above the elevation of A1 and A2. So mean it is we have A1 here and then we have A2. So we have pump, for example, and then this will bring water until the elevation of 100 meters. Okay. So all outlet and inlet are open to atmosphere. So mean the atmospheric pressure is at the outlet there. So if the mean velocity in the pipes A1B and A2B is 2.5 meter per second, so mean we have the velocity at this section. Calculate the flow rate through the pump. So what we need to calculate here is the flow rate that flow inside this pump. The pressure difference across the pump and the power consumed. Take the pump efficiency as 75%. So the pressure difference means if you check the pressure here, so what is the pressure between inlet and outlet of the pump and the power consumed. So I think you know that the power here, so it is equal to rho GQN H head of pump. So take the pump efficiency as 76%. So I think you still remember how to use the idea of pump efficiency in your calculation, because in fluid mechanics 2, we already learned about this one. So first we calculate the flow rate through the pump. We know that the pipe A1B and A2B are in parallel. So means that we need to add the flow rate for each pipe. So we have a certain amount of flow rate here and another amount here. So when the flow is merged at point B, so we just add these two value. So because it has same velocity, so we could calculate by using this continuity equation, and then we could get that the flow rate is equal to 0.982 meter cube per second. So and then for the pressure difference here, so we need to determine the total head loss first. So we calculate the losses before the pump and after the pump. So means that here we have the series. So and then here we have the three parallel pipe here. So we calculate that. So and then by using the previous equation, so we found that the losses before the pump is equal to 0.3635 Q square, and then losses after the pump is 13.923 Q square. So and then the total losses here, so we add these two value, so we get the value of 13.777 meters. So and then we could write the energy equation. So this equation is Bernoulli equation. I think you could write this equation, means you need to compare 1 point before the pump and 1 point after the pump here. So we have pressure, velocity, and Z. The head of pump need to be added in the inlet region, mean that at the beginning here, and then we have pressure, velocity, and Z, and we have a total losses here. So and then because it says that the pressure is atmospheric pressure, so we could neglect the value here. Okay, so and then so because we already calculate the losses, so we add the value of losses here 13.7, so we could add it here 13.7, and then we imagine that the velocity and the height first, the height z is can be cancelled, because if we see here the B to C here, so the length is 300, the diameter is 0.75, and the friction factor is this one. So means that this point to this point will use this type of pipe. So means that the diameter is the same. So means that the velocity is the same. So we could cancel this one. So and then we could okay, I'm sorry. So we cannot cancel the z here because as mentioned in the question, so we have the height of the is the 100-meter height here. So mean that the z we just compare from this point to this point. So means that the velocity here is 0. So and then so we just assume it is equal. So we could cancel the velocity. So we only have the value of z here. So and then the z is 100. So and then we have the losses. So we have the 100 plus losses here. So we have 113.7 meter. So and then we could calculate the pressure difference across the pump. So by using the idea of this one, we know that the pressure is equal to rho GH. So mean at this situation, so we have the rho here is the water, the G is the gravity, and the head of pump is 113.777 meters. So we could calculate it as 1116.15 kilopascal. So and then we could calculate the power consumed or power inlet. So power itself can be calculated by using the equation of rho GQHP. So and then but we have efficiency of 76%. So efficiency means power out divided by power in. Okay, so here what we calculated here, the power consumed means the power inlet. So we change this equation, so we have the power in is equal to power out divided by the efficiency. So we get it is around 1.442 megawatt. So means that we need to supply 4.442 megawatts, because not all the power here can be converted into the head of pump here. We need to spend 0.24 or 24% from this amount to overcome the resistance, because it is only 76% from this amount of energy will be converted into the pump, into the power that used to lift the water.